Good afternoon, everybody. I'm Gabriele Luzzani. Thank you for the introduction. I'm a PhD student here at the Politecnico Torino, and I'm the second year of my PhD research. My research project aims to study and develop a real-time pilot performance monitoring system. Due to the nature of my research project, our research team is composed by different competencies merged together. In fact, on one side there are me and the full professor Giorgio Guglieri that represent the aerospace part of our research team. And on the other side, there are the full professor Daniele De Marchi and the postdoc Irene Buraioli that represents the bioelectronic and bioengineering part of our research team. I structured this presentation, this speech today, starting with a brief introduction about the importance of pilot performance monitoring in the aviation sector. Then I'll present you our approach to this topic. Then I present the data acquisition and data analysis pipeline that we are following in my research project. And then I conclude with the next step, research preliminary results that we are obtaining from our project. So I think that not most of you know these data that are very important in the aviation sector. So the fact that the 90% of the fatal accidents that occur in aviation are due to human errors. And it is possible to demonstrate that the 60% of them occur during the highest workload phases of a flight mission. So for example, our takeoff or landing. And if we think in a possible future transition towards the so-called single pilot operations, so a condition when there is only one pilot on board an aircraft respect to the actual condition when there are two pilots on board an aircraft, obviously these data acquire a more dangerous perspective. A transition towards a single pilot flight has mainly two benefits. The first one is an economic benefit. In fact, it is demonstrated that it could halve the operational cost, especially in short and medium range flight routes. And on the other side, this transition could help us to cover the pilot shortage that we are living now, and it is forecasted to grow in the next few years. However, to reach this goal, there are some problems, some constraints, regulatory problems, ethical problems, and technological problems. And one of them is represented by the development of a collaborative and autonomous digital cockpit assistant that can replace the figure of the actual co-pilot. And it is necessary in order to guarantee the same or higher safety level that is regulated up to date in the EASA parts, that they are the European aviation rules. And to do so, it is necessary that this digital cockpit assistant will be continuously able to monitor the pilot's state of health and his or her cognitive workload and stress level in real time. And it is on this topic that my research project is focused on. In aviation, up to date, there are mainly three ways to assess this problem. That are subjective evaluation, that are essentially post-performance questionnaires submitted to pilots, but obviously they lack of the real-time capability. Then there are behavioral measurements, so essentially a comparison between a predefined mission plan with the actions that the pilots perform during the flight mission. But this approach lacks of the scalability. Scalability features. And then lastly, there are the physiological measurements. So essentially infer the workload condition and stress condition of a pilot during the flight mission, starting from the analysis of his or her physiological signals. And it is on this topic that we are focusing on our research. In particular, we are adopting a multimodal approach, so we are considering all the physiological signals that in the literature demonstrated a relationship with the variation of stress and cognitive workload in order to infer from them the aforementioned workload index. And we want to integrate this physiological data together with the aircraft data provided by the system. In particular, the signals that we are considering are the skin activity, represented by the electrodermal activity, then the brain activity through the functional near-infrared spectroscopy, then respiratory measures through the detection of the movement of the chest, then heart measures from the ECG and the photoplethysmogram, the PPG, body temperature, and then lastly the eye activity. That is an important feature that is gaining more and more interest in the aviation sector in the last few years. So, starting from these signals, we want to extract all the features that in the literature demonstrated a relationship with the variation of stress and cognitive workload, then through machine learning algorithms, select the most significant features related to our approach, to our environment, and then build on them a classification algorithm that is able, starting from the physiological signals, to give us the workload index that is our output. So essentially this is what we want to do. What we did until now, it is the second. In fact, we have to take into consideration the fact that in the literature, a reliable and well-established solution that is able to provide us the workload index starting from physiological signals up to date is missing. So we decided to start from a small subset of the aforementioned signals represented by the PPG, so the photoplethysmogram signals that is related to the heart activity, then the EDA that is related to the skin activity and the body temperature during the performance of two different tests. The first one is named the Stroop test. That is a test developed by psychologists and researchers and is very famous in this research field that is able to modulate different stress levels. Then there is the handback test, visual and auditory, that is also in this case a well-established test that is able to modulate different cognitive workload level. And then we asked also to our volunteers to perform some self-assessed questionnaires at the end of our test. And we was able to perform this test on a population of about 31 volunteer subjects. This was essentially the graphical interfaces of our tests that some of you know very well. So in fact, our test was structured with a brief, relaxed starting part, where we acquired the baseline, the physiological baseline of our subjects. Then we asked our volunteers to perform the Stroop tests that was divided into three different stress levels with an increasing trend of difficulty. Then another relaxed part. And then we asked to our volunteers to perform the handback test, visual, auditory, and visual and auditory merged together. Each of these three different tests divided into three different difficulty levels in order to acquire our physiological data in three different conditions. Then, once acquired our signals, we processed this data. In particular, for example, for the PPG processing, we adopted a classical processing of our data. So starting from the raw signals, we remove noise, we window the signals in order to extract some features related to the PPG shape itself, the heart rate and the heart rate variability, both in time and frequency domain. It is important because, as you can see here, it is possible to observe that some information related to the stress and cognitive workload are contained both in time and frequency domain. For example, here I have reported the BPM trend, so the beat per minute trend during the execution of the test, and as you can see, only with a simple visual representation. For example, here it is clear how during the Stroop test there is an increasing of the BPM mean, then followed by the decreasing during the rest phases. And here, also in this graph, you can see that there are visually three different phases that present different colors, 1, 2, and 3, while two different parts were these colors are different. This is a spectrogram, so the representation of the frequency contents of the BPM during the execution of the test. And this blue part represents the stress and cognitive workload tests, while this part represents the rest phases. And so it demonstrates how something is changing during the stress and cognitive workload phases and respect to the rest phase. And what is changing is the ratio between the low frequency and the high frequency contents. Then we followed a similar approach also to process the EDA. Also in this case, we started from the raw signals and we arrived to extract features related to the slow components of these signals, that is named the skin conductance level, SCL, and the fast component of the EDA, named the skin conductance response, SCR. And then we complete this preliminary signal processing part with the extraction of the features related to the temperature. In particular, we extract features related to the temperature itself and its first derivative. So essentially, we build our dataset. The strategies that we adopted to process these signals was the following. So we decided to study the correlation between our dataset that was represented by the features, the 43 features that I present to you, I have just presented, evaluated for the 28 people, because we have to exclude 3 people due to some problems during the acquisition session, calculated for each different test phases, that for each dataset separately. So the Stroop test and then back tests. And we want to study the correlation between these features with the results that we obtained from the subjective questionnaires that we asked to our volunteers at the end of the test, that was related to their subjective perspective of stress and cognitive workload during the execution of the tests. And in particular, this self-assessed questionnaires was divided into a 5-level scale. The first step was to investigate essentially our dataset, and we compared the expected trend of our populations with the expected trend of the literature. And we did this visual comparison for each of our 43 dataset features and their literature expected trend. Here they are reported only 2 examples, but we did for all the features for each dataset. And then we started with a preliminary machine learning analysis of our dataset. In particular, for example, here I have reported the results that the best performance combination between the feature selection algorithm together with the classification algorithm that we have from the Stroop dataset, so the dataset related to the stress conditions. And for example, we obtained in the principal component analysis PCA as the best feature selection algorithm, together with the logistic regression as classification algorithm. And we obtained a F1 score of 70% on our Stroop dataset. And for the end-back test, we obtained the best combination of features feature selection algorithm together with classification algorithm from the univariate feature selection, in particular the select key best, together with the logistic regression. And in this case, we obtained a weighted F1 score of 81%. Obviously, these data are not so high F1 score, because essentially we have a small data set. So we acquired only data for 28 people. Obviously, this approach needs to have a bigger data set. In fact, the next step that we have already completed was to acquire more and more data on a bigger population. We reached also 100 people in our tests, and then build a more accurate machine learning predictive algorithm. But these preliminary tests was important because they demonstrated the functioning of our pipeline, of our workline pipeline. And then the next step once also performed this same approach to a bigger data set, is to take the predictive model and put it into an aviation context, an aviation environment. In fact, we want to perform some flight tests on the A320 simulator that we have here at the Politecnico in order to acquire this data on some pilots during the execution of a simulated flight, and then take this approach into the aviation sector, because it is the aim of my research project. So with this, I thank you, and I'm here for questions.